3.9 derivatives of logarithmic and exponential functions. So we have to review quickly just exactly what is exponential functions. It is when we have a constant base, and we're going to start with base e to the x. So our unknown is the exponent. And then this is a function that looks like the pink curve. That's how they graph. This is base e. And we see that it always goes through the point 0, 1 in its parent function form. And then we have its inverse function. Remember, inverses always reflect across the y equals x, the green line that we have here. And then the inverse function is actually being drawn as this black line, and that's how it reflects. And you see the equation for the inverse, f inverse of x is ln of x, natural log. So a couple things we have to remember. We have, if we're given a function, we're going to say y is the exponent. So let me rewrite this. E to the y equals x. This is the inverse, but we want to solve the equation for y so that we have our function notation. Notice these are both functions. They pass the vertical line test, but in this case, to bring our exponent down, we take the natural log of both sides, or we can also say we can write this in the form y equals ln of x. So remember, we can always say from here, base exponent equals the answer. So the other thing we have then in our setup that we want to do for this section is, what if I have a base that's not e, it's some other number? We always use it with a base b to the x. And it says here in our line 3, for all real numbers x and b greater than 0, we can change the base. We can change it from a base b to a base e by saying e to the ln of b to the x, and using our power rule, the exponent of x comes before the ln, so we have e raised to x ln of b. All right, so this is an important property that we need to use. It's really technically called a change of base. So given here, this graph shows our function, the inverse of an exponential, so y equals ln of x, and the pink graph is its derivative. But how did they come to that derivative? So if we are going to go ahead and say, given this function, x equals e to the y, and we want to try to implicitly differentiate both sides of the equation, I would get 1 equals e to the y, and because of the implicit differentiation, we have to do the chain rule multiplied by dy dx. And then from here, I'm going to be solving for the dy dx, and I have the equation 1 over e to the y. But that was our original functions. We want this in terms of x. We're taking the derivative of y with respect to x. So I'm going to go ahead and use this equation here in our first line to substitute back in for our e to the y, and I have 1 over x now. And that's our derivative of a natural log. And that's our theorem 3.17. So the derivative of natural log is 1 over x for all x greater than 0. And remember, why is it greater than 0? It has to be in our domain. Back to our original function for exponential functions and taking its inverse, we have to keep it real, and it always has to be greater than 0. Our second derivative in this box, though, is saying the natural log of the absolute value of x is still, the derivative is 1 over x. X can't be 0. So here we go from here. Why is that possible? Well, just think about it. What if I had a natural log, and we say of a negative x, and we take the derivative of it, it would be the 1 over the negative x, and then the chain rule said we have to take multiplying it by the derivative of what's the coefficient, -1, and we still get 1 over x. So even the absolute value, it works the same. This last line in our box is in case we have something like what I just did with the absolute value, but what if it was like ln of 2x? We have to follow the chain rule, so this last one is just reminding us of the chain rule. All right, so let's go walk through some examples. From the textbook, we're going to do number 10, and they want us to find the derivative of x squared times ln of x. And this would also be a product rule. So I'm going to do the derivative of the first function, and then a derivative of the ln. So ln of x is 1 over x, and I'm going to write it as one term together instead of two different factors. So from here, I'm just going to simplify 2x ln x plus x. So I'm going to do a GCF. And there's my final answer for the derivative of this one. Let's do number 13. We want to find the derivative of natural log of sine x. So in this case, I'm going to do the derivative of the outside function, the natural log, and then I'm going to multiply it by the derivative of the inside function. Derivative of sine is cosine, and then I can see here these are factors. I have cosine x over sine x, which is cotangent x. And there's my derivative of that one. Let's do next number 15. And I'm going to take the natural log of x plus 1 over x minus 1. And in this case, I've got a quotient rule happening, and I'm going to want to set up to my side. My high function is x plus 1. Its derivative is 1. My low function is x minus 1, and its derivative is 1. And then I'm going to be using a combination of derivatives here with a quotient and then for the inside function. So I'm going to go ahead and say that the derivative of this is going to be 1 over dealing with the ln. And I realize I have a missing parentheses in here. Okay, and then I'm going to multiply by the derivative of the inside, which is going to be following the quotient rule. And then from here, it's really messy and it becomes just a matter of simplifying this expression. And it does simplify into x minus 1, x plus 1. And I'm going to multiply here at simplifying this second factor, which simplifies down to a -2 over x squared minus 1. I had a difference of square factors. I went through the multiplication distribution to simplify the denominator. Let's do one more problem. Number 19, we want to take the derivative of the natural log of x. So we're going to follow the chain rule for this one also, and it's going to be the derivative of the outside function times the derivative of the inside function. And this is our answer for number 19. All right, so if I look at a couple of other exponential functions where it's a base b, and I see that in our first picture, the base is 1.29 to the x power, and we see its derivative. And we haven't said why yet. I see in the bottom of the screen, but look at how they graph the derivative. And then the second picture, my base is 6.57 to the x. And notice that the key thing is here is looking at paying attention to the slope, and we're always focusing on this point 0, 1, and what's happening here. I did bring in, notice how it is on either side depending on what the base is, and notice how when it's a natural base e, we should have a slope of 1. So the derivative theorem for this base b is going to be the base, the function itself, times a chain rule situation, which is ln of b. We could put this in terms, if we, because of that change of base, it comes from b to the x is x to the e to the x ln of b, and then using this property to prove theorem 0.18. Let's do some examples. Number 23. I'm given the function y equals 8 to the x, and I want to find its derivative. It should be 8x times ln of 8. But if I want to try, let's do one more that's maybe not as simple, where I'm given y equals 5 to the 3t, I have to deal with that 3 coefficient of the exponent. So for the derivative of this one, I'm going to have 5 over the 3t times 3 ln of the b, the 5. Let's do number 25. Having a multiplication constant out front, we can deal with this the same way we've done any other constant multiple. So the derivative of this one would be 5 times the 4 to the x, and then we have to multiply by the ln b, which would be ln of 4. And we'll leave our answer like this. Remember, these cannot multiply. They're different actual multiplication factors. Let's do number 26. I have a product rule also going on with this equation. So for its derivative, I'm going to do the, because the exponent is not just x, I have to deal with the negative. 4 to the negative x times ln of b, so ln of 4, and that's the derivative of the first function, leaving the second function alone, plus, leaving the first function alone, derivative of the second function. This is my whole entire answer for the derivative of 26. For 31, I am not going to draw this out, but it's an exponential model that is given a complete chart of information, and they do give us an equation where t equals 10.2 or 10 times 2 to the negative 0.274a. So they give us an equation, they do give us a chart of data, and they want you to walk through this in different processes. But the key thing on this example is it's like the example in the book. Example number 3 on page 214 that I would like you guys to walk through. General power rule. This comes around again, and there's a reason why. In this case, we really want to deal with if we have a chain rule effect, if there's some other derivative out front, it becomes bigger issue. It becomes a messier problem, but it follows everything else we've done before. So let's do some examples. We're going to do number 38, where they're giving it s of t is equal to cosine of 2 raised to an exponent of t. So I'm going to go ahead and take this derivative. I've got to do the outside function, and I'm going to multiply it by the inside function derivative. So using an exponential, it is the function itself times the ln of the base, ln of b, or 2 in this case. So this is my final answer in this one. It could be written neater. In this case, I'm going to leave it as is. Number 39, given this function, this one is pretty simple. I feel that the derivative of this is 2e to the 2 theta, and we're done. Let's do 42. Given the function of tangent of x raised to the 0.74, and we want to find its derivative. So from here, its derivative would be the outside function times the derivative of the inside function. Now this is not an exponential, this is a power rule. So we're going to multiply it and subtracting 1, and this would be my final answer for this derivative. I also want to do example number 43. We're given this function, and we want to find its derivative. So I have exponential function and I have a quotient function. So we're going to do a couple of different things. I'm going to set it up for the exponential, my high, d high, and then my low, d low. And then when I go ahead and set up my derivative, I've got low, d high, oops, that's an x, minus high, d low, all over low squared. All right. In this case, we want to just go ahead and simplify the numerator. And so what I'm going to do from here is I'm going to see that I have a GCF of 2 to the x ln of 2 that I can pull out. Oh, you know, I think the more I think about it, I tried that and I kind of thought it was a little easier to do something else. So before I do that, I'm going to go ahead and multiply these together. So for there, I'm going to go ahead and have 2 to the x times 2 to the x times ln of 2 plus a 2 to the x ln of 2 minus a 2 to the x times 2 to the x ln of 2 all over the low squared. Then from here, I'm going to go ahead and do a GCF. That would be easier then. I can see that my GCF is going to be this term. So, oops. All right, it's not a GCF. I can see that it's positive and negative and they reduce to 0. And then I'm only left with this middle term, 2 to the x ln of 2 over the quantity 2 to the x plus 1 squared, and that's my derivative. All right, there we go. We got this one. Moving on, we have the derivative of a logarithmic function. So from here, I see that we want to remember a couple of things about log functions. Remember, there's something called the product rule, where if you're given a natural log of 2 things being multiplied, it can be split into 2 separate log functions. We also had a quotient rule. Two functions being divided, we can separate them out. Remember, it's always the denominator in the second term, and it's going to be the minus. And then we had the power rule. Remember, that's my favorite thing about logs. Power rule said that if we're given to an ln or a log function of some answer part of the equation raised to an exponent, power rule said this exponent can come down as a multiplication factor. So we like using these, and we're going to need to remember these for some of our homework problems. And then it says here that when we take the derivative, the log base b of x, the derivative is 1 over the answer part times the natural log of the base. It also works for the absolute value of the answer part of the equation. So let's go right into some examples. And I'm going to do example number 61, which gives us this equation. And we look at this and we're going, okay, there's something very messy about this one. So before I even decide to take the derivative of both sides, I'm going to go ahead and take the natural log of both sides. So what I'm going to do from here is I'm going to say the ln of f of x is equal to the ln of the right-hand side of the equation. And then from here, I can use my properties that we just did for this side of the equation. I can split this quotient into 2. Sorry. The natural log of 2x minus 4 to the 8th power. I can also then use the power rule in this case. So I'll bring this exponent down as a factor, and I'll bring this exponent down as a factor. All right, so now from here, I have the natural log of f of x is equal to the natural log, or 10 times the natural log of x plus 1 minus 8 times the natural log of 2x minus 4. At this point is when I want to take the derivative of both sides of my equation. And I'm going to take the derivative of this one here. So from here, I have us having d dx of the natural log of f of x is equal to, and then from here, I'm going to go ahead and try to take the derivative of this right-hand side of the equation. So from there, I can see that it should be 10 times 1 over x plus 1. Chain rule would just be a multiplying by 1. And then minus 8 times 1 over the 2x minus 4. Chain rule says multiplying it by 2. And then I can keep going. I'm going to simplify the right-hand side. And then from here, I've got to deal with the left-hand side of this equation. And it turns out I can just go ahead and put this in the notation. It's going to be the derivative of the function over f of x. It's taking the natural log. So from here, long story short, I'm going to multiply both sides by f of x. And then I'm going to substitute in, eventually, the original function for f of x. And I've got x plus 1 to the 10th power over 2x minus 4 to the 8th power. And I'm multiplying this inside, where I'm going to simplify this second term to, I believe it's 8 over, and this was a 4, 8 x minus 2. And there's my answer for this one.